All right. Good morning. So, I wanted to show a couple things before we get into the lecture today. First of all, on our Moodle page, we now have um, a link to the YouTube playlist that I will assemble. I'll basically upload the lectures weekly. So right now, there's none there, but you could follow that link. I've made a playlist there. So if for the typical lectures, that's where they'll end up for the class. Um, last last lecture, we can see. Well, right now you can see I'm live on the Twitch page, so that's going to get a little trippy as we watch that continue. It's a lecture inception here. So maybe we'll stop that for a moment. So if you had to watch live, you could technically watch there or catch up on a previous stream there. And I'm just confused looking at it, so I'm gonna stop that now, I think. But that's a live stream. That's where I'm streaming, just because that's what was convenient to figure out during the pandemic. And then basically I download from there, upload back to YouTube. I was checking on the audio yesterday. It looked quite quiet, but I was recognizing the voice quality was with this little microphone was a lot better than my webcam. So I'm just going to try to boost up the signal as much as I can and put it closer. So I think that'll be sufficient. You could hear my voice from last time if you turned the volume way up, but it was not ideal that time. Okay, so hopefully better this time. Sorry, I can't do anything about the temperature in here. Okay, so today, really what I want to do is talk about some fundamentals that I'm guessing you've all had in some form or another. So one of my goals here is to help take anybody from different backgrounds and kind of unify our skills so that we can solve more complicated problems and understand, okay, why is it that we are taking this approach or that approach or whatever. So some of this is going to be reviewed. I'm not going to spend a whole lot of time. So what I'll ask you is, if you happen to get confused or be unfamiliar with something in particular, really at any point, please ask. Right. So not everybody has, let's say, an engineering undergraduate degree, for example. So some of the concepts that some of you've seen for years now may actually be a little bit new to some. Okay. So the first thing to say then about the matter is units. Whenever we're solving problems, units are really, really important, meaning like, okay, is it grams, kilograms, grams per liter, grams per cubic meter? What are we talking about here? That's a way we can kind of remind ourselves what's our target. We can reverse engineer problems to say, oh, okay, well, we need an answer with this type of unit, so how are we going to get there? Even if you kind of forgot the typical steps of a particular type of problem, unit analysis, informal or formal, is a great way to try to get yourself back on track and to get something that's an answer that's meaningful to some design problem. So the premise of basically all of our design for water and wastewater treatment is conservation of matter. A lot of times we're talking about conservation of mass. Sometimes we'll be doing a balance on, let's say, number. So we might have a number of pathogens. So we're not really too concerned about the mass of them. You could maybe think of what mass of viruses or bacteria or something would be in a stream of water, but we're not actually too concerned about the conservation of that in terms of mass, so much as, well, how many have we killed? How many are inactivated and no longer a problem? So I say conservation of matter to kind of catch mass and those other cases. Okay, so with that, I do expect everybody to be familiar with SI prefixes, suffixes, or not suffixes, prefixes, both larger and lower than the standard. So if that's any trouble, go take a look, study all that. really most of what we would use is kilo, maybe mega, deci, centi, milli, micro, nano, that kind of stuff. I think you're probably all familiar with that. Okay, for a given mass balance, so we say a mass balance, that term, really what we're talking about is when we are going to design some problem or solve some issue regarding water treatment, we want to know what's happening to the mass. So we define a discrete control volume is what we'll call it. We'll talk about that in a minute. And basically then we're tracking what's happening to the matter inside of it. If we take viruses, for example, that'll be, I guess, a number analysis. We want to know all of the viruses that could possibly enter this water or exit it. Now I've got it in a presumably sealed bottle, so we would say there's no entrance or exit, so whatever's happening to them is going to be due to some reaction inside of here. Maybe I'm shining lasers that, in the UV range and it's killing, zapping the viruses, or maybe I'm heating it. Whatever the process, we're looking at it in terms of some action within that system. Now that'll change if I pipe some liquid in and having some liquid out, right? So we can conceive of different setups here, but what we're doing is we're tracking either mass per time or sometimes like the number, like a number concentration over time, what's happening in there, right? So that's what we are referring to when we're saying, let's do a mass balance, right? We are saying, let's track that mass or number over time and say, well, can we find some equation for that given some inputs perhaps? In this case, if I am adding something into it, we'd subtract any outputs if we're extracting some viruses somehow, plus whatever kind of a reaction is happening, which could be a plus or minus, that could be creating or destroying viruses inside there, right? So that's sort of the big picture premise of when I say mass balance. So, many of you have had that or repeatedly. I just want to make that very clear. That's kind of what we're talking about, and we're almost always doing a something per time type of analysis, because what we're interested in is what's happening with this over time, or if we've reached a state where it's steady, a steady state. We'll get to it, but that accumulation, if we're destroying some viruses all the time and we're passing some water in and out, we'll get to a point where if we have the same amount coming in over time, we could have a steady 5 living viruses in this 1 liter at all times when we had 500 coming in, something like that, right? Okay, so that's sort of the big picture essentials for mass balances. And as I said, that gives us a tool to understand the fate of that mass or matter in a system. So to be a little more technical and derive a bit more from what we were just saying, we'll call it an accumulation rate. What's happening inside our volume, we think of it in terms of how many are accumulating. So if I had bacteria growing in here over some time, there would be some accumulation. Given that it's just a sealed bottle in this case, that may have, perhaps the bacteria are doubling every 4 hours, right? That would give us some understanding of how are they accumulating. We could predict then, assuming they're going to have enough nutrients for that, what does it look like in 12 hours, right? We could tangibly say, okay, well, that's where it's going. So in that case, the accumulation rate would be dependent on how many are in there and would look something like a first order growth rate equation. We'll come back to that and explain that in one of the next lectures a little more clearly. But so what we'll look at as an accumulation rate is going to be mass per time, okay? And usually we'll say within some volume. So a lot of times we'll call this, like this will be in some volume, and I'm going to, a lot of times what we're looking at truly is actually concentration per time in a volume, right? So concentration over time multiplied by a volume of my bottle, let's say, gives us the mass per time. Okay, so that's normally how we look at it. So 5 bacteria per liter, doubling every so often, gives us, after that amount of time, 10 bacteria per liter. And so then, not mass, but number there. So if we take a look at an expanded mass balance, that would be the left side of the term is within that volume that we're looking at. Here's the accumulation rate. Then we can relate that and say, well, that has to be equal to whatever's coming in, whatever's going out. So it's always that balance of what's in there. We know something about it, or we're trying to figure out something about it. That's balanced against what is happening to that system. So if we had an input to a vessel, output that has some volume, and we have some flow rate coming in, flow rate going out, a concentration of some species I, and I'll say not for initial here, and that same concentration of CI after whatever reactions might be going on in there. That would give us an input, a reaction term inside, and an output. So then the accumulation rate here, we could say, would be equal to that the input rates, and by the way, we could have multiple. That's certainly possible, and we could have multiple out. That's all absolutely possible. The first drawing there was kind of the simple version. So what we can say is all the input rates together minus all the output rates plus all of the reaction rates, and I'm going to say plus the growth rates here. So, and then minus the decay rates. Okay, so you'll notice I went ahead and wrote them all as rates. So that means each of these terms have to come down to a mass per time. And that makes sense because we have to keep the units constant. Here's again about the units. We can check to make sure that we have appropriate terms here. Maybe we forgot exactly how to derive that first order rate constant or whatever that's going to go into this rate. Well, we can double check that at the end of the day, we're comparing mass per time over here. And we could maybe check that our flow rate times the concentration is a mass per time. So that has to match up with our rate equation over here. So if we're not getting mass per time with what we remembered or we thought for that growth rate, well, maybe we have to remind ourselves, oh, we have to do that in the volume. And then that turns out to be mass per time. So that kind of unit analysis will be very helpful. So for this simple system up here, if we don't have those added extras there, what that would look like is a Q times that concentration coming in minus the Q times the concentration of the stuff going out, plus if we have a growth rate or G in that volume, so we multiply it by volume, minus a rate of decay in that volume. Okay, so we will come back and explain a bit more about the chemical or biological reactions or physical reactions that would go into these rates, but this is kind of the simplified view of it. That's what we're talking about with mass balances. So what that provides is a useful tool when we're designing a system. We could say, okay, well, we need to achieve some specific growth rate here in order to achieve our goals. If we wanted to grow bacteria so that they're eating some wastewater, we would design it in such a way that that growth rate is going to be appropriate. Or maybe we have to design the volume given the limits of the growth rates that we know for our bacteria. They can only grow so fast. So we're going to have to make a reactor that has such a volume so that we can, allow for the inputs and outputs to be, to achieve some treatment, right? We would say maybe we know we have some sewer giving us this nasty wastewater, and we need to treat it to some level so that the concentration going out is sufficiently low enough. That means if C in and that Q in is constant, then we have to remove that contaminant with the output, which means we need to decay the contaminant. Well, in that case that I was talking about, that means we have to grow the bacteria. So it's kind of another story, but we could balance it in that sense to say, here's this amount of mass, we need it to go that way. We need to take care of it. Here's how we know we must achieve that with some particular term, and perhaps maybe that decay rate is fixed, and so we have to adjust the volume. That's the type of manipulation we can do, and you'll see this theme in most of our problems, that in some way or another we're looking for a term, and within that term there's a parameter that we have control over. And that's what we're going to be designing. Okay, so I mentioned already control volumes. We have a little schematic here. It's actually depicting a typical formulation for what you would find in a secondary wastewater treatment operation if this was an activated sludge. You've got bacteria growing, typically aeration. There may be some other types of reactors that are set up this way. Followed by a sedimentation chamber. So if we have liquid phase but solids mixed in, then we want to settle out the solids. A system like this, we could draw a few different control volumes to analyze it. So in the first case up here, you see the dashed lines drawn just around this first reactor chamber. We see that there is a recycle line here that we could consider, but right now they're just drawing it there. So in order to define the control volume, typically what we want to do is define I. This is our textbook's definition for some species, some chemical, some bacteria, whatever we're interested in, the analyte. So I drew earlier like a concentration of I. That's what I was referring to, right? So define what it is that we're looking at. So in this case, with the sort of a wastewater example, if we are really specifically interested in the I being like bacteria, we might want to draw it just around this box to identify how quickly are they growing in that particular chamber. Perhaps we're looking at the amount of wastewater junk that's coming in, so maybe that would change the way we want to draw our control volume. Okay, but anyway, so define I, then draw the control volume. Then after that, we want to define all entrances and exits. So in this case, we have one here, entrance there, and an exit here. And then define all reactions, plus or minus. So we might have growth for bacteria and death. That would be very natural. Maybe we realize we could have some predation by other microorganisms if we're getting really into the microbiology. Maybe we realize that in addition to the death, sometimes we get some wastewater that's really harsh. Maybe some industry dumps a bunch of acid and could kill off our bacteria. That would not usually be what we're designing to handle on a routine basis, but we could say, okay, well, now the bacteria are dying at this rate because the conditions aren't good for them. We could conceive of a problem like that. We could look at different aspects, different reactions like that. Okay, so then we would have our growth, our death, and maybe there's multiple ones of those or different causes of the death, right? So there can be multiple reactions. We're just going to define them as needed. So in the second case, we see we're drawing the control volume around this sedimentation basin, including the split off between what we'd call a recycle line here. So that would be one exit, and this waste line would be a second exit, and the effluent line, which most of the water will go out there, would be a third exit, and we have one entrance, right? So we could define it that way and consider only what's happening to our analyte of interest within this space. Lastly, we could define it across this entire boundary, and this is more typical for considering secondary treatment things for wastewater. We have one entrance and two exits. that recycle line is fully captured within the control volume, and so effectively that we end up ignoring it in a manner because it's that recycle line is not sending anything inside or out of our volume that we've said this is where we're interested. Okay. Of course, we would also define the reactions. Just as a side note, in wastewater treatment, we typically make an assumption that since we're not bubbling air through this chamber and it's not sitting in there for too long, we assume there's no reactions. So then we end up ignoring that volume altogether, and it's just what's happening in our primary reactor, and we have one entrance and two exits. So it simplifies our system that way. But that's one of these assumptions that we can make, which is true enough, even if it's not a perfect one. Okay, so just some examples there of drawing control volumes. We'll see this. We'll work through a little problem in a little bit. It's worth thinking about, especially to draft from here a mass balance, right? So for each of these A, B, and C, you could write a different mass balance. So for the mass balance on A, you would say, we could call it that accumulation of C, dCi over time is going to be equal to, in that volume, so that volume times the concentration will give us that mass per time. In that case, we said we had the one input here, Q. Well, that's actually Q plus QR, because that recycle line comes in. So we'd have Q plus QR times some concentration at that point. And I'll just say, we'll call this Ci. Ci, I'll just say Cn. Cn. Okay. So that would be the contribution coming in minus what's going out, and that'll be coming out right here. So I'm just going to call that Q out. So we don't have a name for it, we'd have to label it there. Times C, and I'm just going to leave it as C there, so whatever happens to be exiting. And then plus whatever reaction terms we have in that volume. So plus that volume times any growth rate minus volume times any death rate. Okay, so that would be then a mass balance for this volume on that picture. So we could do that for each one of them. That's probably worth doing, double checking to see, okay, does that make sense for each of these? What does that look like? What happens if you have two volumes? You could think about that. Okay. Any questions, issues with that? All right. So I'd like to go through this example. Great. I hope that was not crazy amount of noise for the recording. Okay, so I'd like to go through this example where, again, we're kind of looking at the same system and probably doing essentially what we just talked about, but with some numbers here. So this is the first example in the book, giving us a chance to say, okay, the very base level topic here, what happens if we put an application to it? In this case, rather than using the wastewater example, they're saying a common approach to soften water, we mentioned water softening last time, is to adjust the chemistry in some tank like that before, and then precipitate solids. Okay, so it's another time where you might have a reactor setup that looks a little bit like this. So I'm going to read through this, and we'll give you a few minutes. I've got a couple more slides here for us to work it through. But I'm going to give you a couple minutes with this after we read through it together to see if you're able to orient your mind on what exactly is it asking for, how do I get there, okay? So a common approach to soften water is to adjust the chemistry of the solution to cause CaCO3 solids to precipitate. As noted, such processes often utilize a flow scheme like this one. New solids generated in the main reaction tank, and then solids are separated from solution in the settling tank after that. However, rather than discarding all of the solids, a fraction of the settled sludge is returned to the reaction tank to provide seed crystals onto which more solids can precipitate. In fact, there's if you have ultra pure water and you try to precipitate crystals, it's pretty hard to do so. They actually need some contaminant. If you've ever done the like at-home crystallized sugar by superheating water, heating water quite a lot and getting a super saturated concentration of sugar, usually you'll dip something in it to cause the crystallization to begin. Because if you use really pure water, you'll have an issue there. Side note, you can theoretically superheat water in a microwave way past boiling point if it's super pure. It's very dangerous. I don't recommend trying it. Because if there's no disturbances, you got a very, very clean vessel, there's a chance that nothing can allow the initial bubbles to form because it's trying to form water vapor in gas form, but apparently that needs, again, some impurity to create the initial bubble. So if you were to do that and then disturb it when it's way above boiling point, then you get a nasty explosion and lots of burns and stuff. So probably don't want to do that. But theoretically, I've heard it's possible. Okay. Anyhow, so the advantages of operating the scheme are discussed in Chapter 9. We'll come to that later in the class. The relevant reaction is calcium plus carbonate gives us that calcium carbonate salt. A proposed water softening process will treat a flow of 3 cubic meters per second of water. The objective is to induce precipitation of the calcium carbonate to reduce dissolved calcium concentration from 150 milligrams to 40 milligrams per liter. Where's my cursor? I lose it sometimes on the screen here. So I'm just going to highlight that. So that's one of the design criteria is to go from 150 to 40 milligrams per liter. The influent contains no calcium carbonate solids. The settling step is expected to be very efficient, so the calcium carbonate solids concentration in the treated effluent is negligible. Okay, so that's talking about what's coming out here of the clarifier or that sedimentation. Okay, so this figure has a specific version, shows the flow streams labeled and some potentially useful control volume boundaries identified. Flow rates are indicated as follows. So we have flows for each of those points. So it says Q1 would be the flow rate right here. Okay, and so on. Assuming the water volumes in the various tanks, the water flow rates, and the concentrations of all the chemicals in the system are steady over time. Okay, that's a big assumption there. Write mass balances using appropriate control volumes to determine the concentration of calcium carbonate solids in milligrams per liter in the pipe between the main reactor and the settling basin. So pipe 3. I'm just going to highlight the pipe 3 actually. So we need it in pipe 3, the pipe leading to sludge processing facility, pipe 6, and the pipe conveying recycled solids to the main reaction vessel, pipe 7. Assume that no precipitation occurs. Assume also that the precipitation reaction occurs only in the reactor and not in the settling tank. So a minute ago, I was just mentioning that In the biological system, we oftentimes assume no reaction here to simplify things. We are given that same assumption for this problem. Okay, so we need to find 3 different concentrations in pipes 3, 6, and 7. We're given all the information we need here. We are also given that assumption that says all these different things are steady over time. So let me take one quick moment before we begin to say, if the volume in this tank was not steady over time, let's say it was decreasing, that gives us a big problem, because then our volume is changing. And that's kind of a difficult thing to handle. If we go take a look back on our typical equations, if this guy is changing, that makes stuff pretty difficult if we've got a reaction going on in there. In addition, when we're looking at an accumulation over time, that mass per time in some system, if we can say things are steady over time, then we can set that to 0. This is the steady state assumption, is 0 equals accumulation. And this steady state assumption is very handy, because that means that we can set everything coming, the input rates and the growth rates will equal the output plus the decay rates. So the steady state assumption here, if we can make it, is very handy, because then we can set apart the system to just have that balance, right? That's part of where that mass balance is coming from, is if we are at steady state, we can set the rates equal. Okay, so we're not talking about the actual mass, but the rates there. So if we can make that steady state assumption, that becomes very handy. So I should have probably had a full slide on this, but this is what we're calling steady state. So when we can make that claim that the accumulation in our control volume is 0. All right. So I'm going to give you a few minutes to start working on that. And then I will join your efforts to do so. How are you feeling about it so far? Some progress? A bit. Okay. Keep working. I'm going to slowly start working on it. First steps in the next slide here. Okay, so we'll start here. Hopefully, you've had a chance to kind of think about and pursue some way to solve the problem. So we're given several assumptions, primarily that the system is at steady state. We're going to assume that it's pretty well mixed. We're not given any information about the reactor being anything weird or whatever. We'll talk more about that later in this later today and next time. But the reactor conditions, we're just told that it's a reactor. Reactions going on throughout the reactor, right? We're told that there's no real reaction in this guy for the precipitation reaction. We're told that this sedimentation chamber is kind of perfect, so no solids make it out. So we can set the solids equal to 0 there. So if we think about the initial task to figure out the solids in 3, 6, and 7, probably the easiest one to start with would be 6, because that's kind of the most exterior. We can deal with the ins and outs for that one, and then we'll use this control volume B that goes kind of all the way to the edges of what we can do. So that's where I decided to start, is to say, well, we have information that there's no solids coming in, there's no solids going out the top, that sedimentation chamber, so the only place the solids can go is here, and we can say that basically those solids are going to be leaving at the same rate as they're being produced, and that's meaning they're being produced at some rate in here. Here's the reaction happening, producing those solids. And so that's what I wrote out. I began with to say, okay, let's do CS. So concentration of solids at 6 is equal to what? So I chose control volume B, like that. And then I said, okay, well, at steady state, we get the 0 for accumulation. We say what's coming in terms of the solids is Q1 times CS1, which goes to 0, minus Q4. So that's the first output would be at Q4 times the concentration of solids at 4, which also goes to 0, minus what's leaving at 6, which is going to be that Q at 6 times the concentration of solids at 6. That's what we're interested in. Trying to solve for that right now. Plus whatever growth rate is happening in here. I think I put a negative there, shouldn't have. So that'll be 0 equals the minus what's going out plus the growth here in that volume. So the growth of solids in that volume. I don't think we're even given a term for the volume here or any indication of what the rate constants would be. We haven't even covered that yet. So I'll stop that thought right here and say, well, we have some other way of identifying how quickly that's going to grow. We need some information on that, because now we have an equation that's basically relating that growth to the exit of solids from that line 6. So that brings us to the prompt that we were given, which was ultimately our goal was a mass balance on calcium 2+, right? Calcium ions in solution. We were told that we start with 150 and we need 40 leaving, okay? And now the calcium ions are going to be dissolved, so the sedimentation chamber doesn't affect them at all, right? So anywhere water is exiting, it's going to be 40 because we've treated it such that there's 40. So I went ahead and said, okay, we can do a mass balance on calcium. Say 150 in, 40 out. The rest is going to be removed based on that reaction, right? So we have, again, that steady state assumption, accumulation in this tank. We're not accumulating more and more calcium 2+ in there, and we're not reaching 0 because we have a constant input. So 0 equals that input, which is going to be 150 milligrams per liter, times the flow rate coming in here. Again, we have that controlled boundary written on the outside of that. So we're looking really what's coming in here, what's leaving here, and what's leaving here, and then the reaction that's happening inside. So looking at that balance then with calcium 2+, we can say that 0 equals 150 times Q1 minus the 40 times Q4, so that's the amount of calcium ions leaving at Q4, minus the 40 milligrams per liter leaving at Q6. And then we have a decay reaction that is removing calcium ions basically to satisfy that difference, right? Because we could, if we think about it, we've got 150 going in and only 40 leaving. The Qs, by the way, the Q1, we could take a look at this as a water balance since we're also not accumulating water, right? Q1 is going to be equal to Q4 plus Q6. So we know that we're removing calcium, right? That there is a reaction removing calcium. That's the whole context of the problem. So that rate then, that minus VRD for the removal of Ca2+ in that volume, we can now set in terms of known quantities. Okay, so it doesn't even matter that we find a rate reaction or any of that. We can use these known quantities of mass per time and get a mass per time for this rate at which calcium ions are being removed. So we will carry forward this calculation in just a moment to see how much calcium ions are being removed over time. Then we can use the molecular weight difference to convert that to the calcium solids, the calcium carbonate. That will give us a way to come back and solve here, right? Because the rate of which calcium solids are growing is going to be, that's the same rate at which the calcium ions are removed, just as long as we convert for the Ca versus CO3. Okay, so let's put in the numbers, and I haven't done the calculations with a calculator myself, so I could use some help with that if somebody doesn't mind. So we'll say, I'm going to go ahead and put, I'll just write it up. Okay, so 150 milligrams per liter times Q1 was 3,000 liters per second, minus 40 milligrams per liter times Q4 was almost 3,000, so 2,916 liters per second, minus 40 milligrams per liter times Q6 was 84 liters per second. All of that, so this is 0 equals all of that minus this VRD term. Okay, so I can rewrite this and say, well, VRD then is going to be equal to all of that when we subtract it, right? So 150 times 3,000. Let me know if you get this number. I'm going to go ahead and start putting it in Excel. So if you get there first, feel free to shout it out. what you guys get? 330,000 milligrams per second. That would be right. So the units there, we're taking liters per second times milligrams per liter, so that should be milligrams per second, which is a mass per time. That's very good. Okay, so we can take this then, that's milligrams, and we can specify this is milligrams of Ca2+. Again, coming back to that concept where units are going to help avoid confusion in any problems that we're working, we can then say, well, if we want to convert that to how much calcium carbonate solids we're producing, we can multiply this by, we would want to convert from milligrams of calcium to moles so that we can get back to moles of, so we can say that's the same number of moles of calcium carbonate and convert that. So we should be able to say this times 1 mole per 40 grams of Ca2+. And then the next step would be to multiply by 100 grams per 1 mole of CaCO3. We could also add in the conversions for milligrams to grams. We'd have to do that for both of these if we want to end up back in milligrams of calcium carbonate solids. Did I do something wrong? What's up?
No, I'm like having a flashback to eVeg 2000 and doing the cation balance, you know, like the NQ.
Yeah.
Is that relevant here?
Yeah. So the questions about like milli equivalents, cations, things like that, it's definitely highly relevant to water softening processes. But in the context of this problem, we're assuming all of that's happening, right? The chemistry otherwise is taken care of. We'll come back to that when we do cover water softening and precipitation reaction. So basically, the amount of charge in solution, we have to have a net charge of zero at all times. That's kind of a principle of ionic speciation. So there's something in the chemistry that's being done that allows us to remove that 2+. And in this case, the CO3 is 2-. So each CO3 that it binds with is balancing that in some sense. Now, there's different manipulations and stuff we can do and stuff, but this is before we've even really talked about rates in the context of the class. So you're exactly right, but we'll get there. And for the moment, this is we're just taking, I guess, a thorough approach to say, okay, well, here's the simple case, and here's how we can look at it, a word problem that should be more complicated, that should have all these other caveats, but we can deal with it on the simple basis of here's some units. As long as we keep the units and keep these assumptions in place, we have a path forward. So it's a good thing to keep in mind when, you know, I have not expected you to learn anything about water softening, hardly a thing about mass balances, but we can have some approach we can see on solving a problem with a reaction term and all of that, right? This is not, the point is like, it's a way of thinking about it that we need to develop and build that skill, but it's not, it doesn't require, you know, rocket science level of technical information. It's getting ourselves trained to think about it in this manner. Okay, so I'm going to shortcut here and not worry about the moles, the milligrams to grams back, because it's just going to go right back. And so if we do this, essentially we're taking that 330,000, multiplying by 100, dividing by 40. So we'll say this times 100 divided by 40 is going to give us 825,000 825 milligrams per second of CaCO3. And if we check ourselves for a moment, we do recognize that calcium carbonate is heavier than calcium itself, so that does make sense it went that direction, right? Okay, so that gives us, for now, that just gives us this term, right? So that's VRG for CaCO3 equals that. Okay, so all of that to get us back to that initial part of the problem here. So we say that VRG is equal to that. So that means the CS6 is going to be equal to that number divided by the flow rate at Q6. Flow rate at Q6 was given as 84 liters per second. So we'll go ahead and write CS6 and come back to our Excel here and say that divided by 84. So 9,821 milligrams per liter of CaCO3 solids. Should be the answer to that part. Does that make sense? Any issues? How far along the thought process did you get? Did you start with C6 or did you start with one of the other points? Yeah.
I think the 150 milligram per liter as Q1. But my challenge now is you said accumulation is equal to 0, which is equal to 150 milligram per liter by Q1.
Yeah.
Minus 40 milligram per liter Q4.
Yeah.
Minus 40 milligram per liter Q6.
Yeah.
So the 40.
Yeah.
I don't understand.
Okay, good question. Yeah, so that's coming from when we were told here the concentration. So the objective is to induce precipitation. So we're going to precipitate these solids in order to reduce the dissolved calcium concentration from 150 down to 40. And if you think about it, since it's dissolved, the process that changes the amount of solids, which is the precipitation and sedimentation, does not affect the dissolved. So dissolved should go straight through. So if there was no reaction at all, we would have 150 here, 150 here, and 150 here, right? It's just we're splitting it to two ways. So the fact that we have a reaction means it's not 150, it's something lower, and we're told that it goes down to 40. That's our objective. To have 40 coming out here is the whole purpose of this reactor. But that also means that since it's just splitting the water in two directions, and it's not changing, it's not like a membrane or something that will change the concentration of the dissolved stuff, that also means we have 40 coming out here. Does that make sense? Okay. Yeah, so that's exactly the type of thing that, like I'm saying, once we get in the framework to think about it in this manner, we can identify these features and design accordingly. Yeah.
So if the 40 doesn't change, then wouldn't there be also 40 in like the recycle line, and that like we should account for some dilution?
Okay, so that's a good question. So since we've got 40 that has to be what's exiting here, yes, there would also be 40 here. And the question is, then aren't we diluting what's coming in two, right? Because we have 40 here and 150 coming here. You're exactly right that is diluting it. Not by a whole lot. We'll see. I mean, C7 we could take a look. It's it's enough to dilute it a bit. However, we've drawn the control volume outside of that, right? So what's really convenient about the control volume analysis is we can completely ignore that because that 40 coming in the middle is not an entrance or an exit to the control volume. So if we use the control volume A here, it might be a problem, right? Because then right here is entering A, here is entering A, and here is leaving A, the control volume A here, right? So that would be a problem, and we'd have to account for it if we were using control volume A. Okay, that's good questions. All right, so that gives us CS6. We said, I'm just going to go ahead and write that up again. That was 9821 milligrams per liter of CaCO3. Okay, so from here, it should be a little easier now that we've had a way to deal with the reaction term. So from here, should be a little simpler. Let's see, we also need CS7 and CS3, right? Okay, so CS7 should be pretty straightforward because that's actually going to be the same as CS6, right? This is a line that's splitting the recycle, and whatever is going out this side is also the same as going out this side. So CS7, this should be equal to CS6, which is 9,821 milligrams per liter CaCO3. Then we're left with just CS3. And by the way, if you wanted to, for CS7, you could look at it as if you're drawing a controlled volume right around here. You could do it as simple as that, right? You know you have something coming in, something going out here, and something going out here. And the amount of water doesn't change. You know, you're just splitting it into two directions. So you could use that if you want. Yeah. Yeah, it is, but the Q5 is going to be equal to Q7 plus Q6. That's what I meant by the same amount of water, right? You're not creating or destroying water when you split it into two ways. So we're going to have a balance of water, and again, it's a process that's presumably not changing how much solids are going one way or the other, right? It's just a pipe juncture, so it shouldn't be unless something bad's happening with that juncture. Okay, so CS3 then. We're looking for this guy. That means we do need to use control volume A. So here we're going to take a look and say, well, again, we're at steady state. So we're going to say 0 is equal to what's coming in. So that'll be Q1 times 0 minus what's leaving, Q3. Yeah, sorry. We have another input, which is the Q7 like we were talking about earlier. So input Q1 is 0, input Q7 is going to be that guy, the Q7 times C7, which is that 9,821. And then the output is CS3 times Q3. Okay, and we are given a Q for 3. So at this point, we put in the numbers and solve, right? We have about 1 minute left in class or less. So let's just go over to Excel real quick and see if we can do that. Okay, so I'm going to say the CS3. I'm going to separate the terms in my mind. So we're going to say CS3 times Q3 is equal to Q7. So Q7 is 240. We're going to multiply that by that 9,821. And then we need to divide that by Q3. And Q3 is that 3,240. So if I've done that correctly, then the concentration of solids leaving the tank there is 727. It should be less than the point where it gets concentrated, right? So the concentrating effect should increase that concentration, and that's true. So I think that's believable enough, 727. And we can check how the book did the solution, how it describes it. Hopefully they agree with my methods here, or hopefully I agree with their methods. Okay, so that'll be all for today. We've got a few more slides to talk about kind of what happens when you have other physical transport mechanisms. It's not going to be the focus of the class. It's going to be more on kind of having a deep understanding of this type of stuff as it applies to different systems. So that'll be it for today, and I'll see you guys on Tuesday. Any questions before you go? All right. Have a good weekend.